Hi guys, welcome to week 6, day 1. Our topic for today, primary topic for today, is the midterm that will be on Thursday. It'll be a 24-hour window. You can start it's not going to be during class time. You have a 24-hour window to start the test. Once you've started it, you have 2 hours to do it. The format of the test is there will be an online section in which there will be some multiple choice questions. Explain to me what this assembly code is doing. Questions about the caching hierarchy, and questions about bitwise operations. And so your topics for the midterm are going to be assembly, because that's mostly what we've covered in this class so far. Bitwise operations, and the memory hierarchy. So, one note for Windows 10. Okay, so let me pull up some notes on this. New page. This could be 2:16:21. Alright, so there will be a Canvas section, multiple choice, and fill in the blank. On the topics of assembly, on the topic of caching, and the topic of bit operations. So, what do you need to know about assembly? Alright. Better curly brace. There we go. Alright, so you need to know add, subtract, multiply. You need to know branch less than, branch greater than, branch with link, and all the variations thereof. You need to know comparison. What else do you guys use? Load, LDR, row major ordering, it's got a new mouse, and I think this scroll is set up too high. What else have you guys done in assembly? Speed, pointers, 6 lines at a time. That's better. Okay. Yeah, branch with less than, branch with greater than, branch if greater than or equal to, branch with link if equal to. There's like, a lot of variants of this, etc. Compare, and also the S suffix, add and set, subtract and set. Yep. Load, so load, from an array, load into register 5 from register 6 plus register 7. There's a lot of variants of this, and you don't need to know them, because again, what I primarily focus on in this class is the basics. I have a less is more teaching philosophy, where I teach the absolute minimum that you need to do an assignment, and if you want to do a cool trick to save yourself a line of code, like with the -s suffix, or with there's write back and things like that, you can figure out how to do that basically on your own. Okay, you don't need to know the exclamation mark suffix for this. All right. Anything else you need to know? So it doesn't seem like very much, is it? push and pop, I guess. You know, how to function, right? That's something you need to know. You know, push, pop, how registers are passed. How registers are passed to and from. Okay. So registers 0 through 3 are used to pass parameters to a function, and register 0 is used to return a value from a function. You don't have to worry about using the stack to push additional parameters on. It's fine. Yeah, I think that's about it. Right. Power of rot 13, yeah. I did that to hide strings that you guys couldn't find in the code where it was saying different things, so you can break on them. For locksmith, I think one of the best approaches for that is just to find where my string is that's saying things like, you know, welcome to the program or whatever. Rot 13, you can rot 13 the strings, and that will reveal, you know, where it says welcome to the program or whatever, and then you can set a breakpoint on that. All right, so that's the easiest way of doing locksmith. If you knew what you're doing, you could probably break each of those programs pretty quickly. If you guys think of anything else in assembly we've talked about this semester, I think that's about it. I mean, I guess, you know, if statements, how to do if statements, how to do loops, how to do functions. Yeah, which is just combinations of the previous things. Labels and the dot global. Right, so labels in the dot global directive. Okay, so the format of the midterm. There is going to be questions on Canvas, multiple choice, fill in the blank, on these topics: assembly, caching, and bit operations. And then there will be a coding section. And in the coding section, you will need to write code, and you'll need to debug code. Okay. There will be one function you have to write, one, and there will be one function I will give you that is not working properly, and you must debug it. Shifting won't be on there. Yeah, that's bit operations are part of shifting. Yeah. Shifting and or etc. That's the topic of the worksheet. So the only thing you guys have to do between now and the midterm is the worksheet. So that is on Canvas. It's called the Bitwise Operations Worksheet. And we'll talk about that in just a little bit. I'm going to go over the midterm first. So the multiple choice section will be worth 50%. And the coding section will be worth 50%. So that means this section is 25%. Okay. So you're gonna have to be able to write assembly code from scratch, write a function, you know, I don't know, be able to do something on the lines of write, you know, Fibonacci or prime testing or averaging numbers or things like that. Okay. Does it sound too crazy? No, I mean, I can make it harder if it seems too easy. No, it's not designed to be hard. Like I test you guys on the things that we've been doing, and the assembly is what we've been mostly doing. So I'm going to review caching and I'm going to review bit operations right now, because those are things we've only touched on lightly, and things we've done lightly, students tend to not remember very well, because you tend to remember things that you've done, right? And so if you've been doing a lot of assembly, then you remember assembly, right? So this kind of stuff should be fairly, good for you guys right now. Coding section is similar to the ones we did for 40 and 41, but in assembly, yeah, exactly. Except you're actually gonna have to write a function from scratch versus debugging code. And once you start the midterm on Canvas, you have 2 hours to do it. And so the format is you have a 24-hour window, and once you start, you have 2 hours. Okay, and that includes the coding section. So I'll be checking the timestamps on the server, and so basically whenever you start, you should be able to blow through the multiple choice pretty quickly, and then you should have enough time to do this section here. You hate feeling rushed? Yeah. They're not, like I said, they're not going to be very complicated things. Okay. And so you have a window of time to begin, and then there will be no input tester. So test your code. Homework is usually harder than the coding part of the test, yeah. Yeah, because I want people to be able to do it, And yeah, being able to code under time pressure is actually a really important skill for computer science people, right? So, in the real world, you've got deadlines and things like that. So, I'm going to try and not make this multiple choice section very long, so that you can jump into the coding. Okay. The debugging is usually one compiler error, and one logic bug. So it's usually 2 quick changes and you're done. Invert a binary tree in 30 minutes, yeah. I don't understand why that's considered a coding interview. Okay, yeah, so that's the midterm. So let's talk about caching again. Let's talk about bit operations. So try that again. Okay, caching. So the type of caching we use in this class is not obviously accurate. I do this so that you can understand caching and also understand that every CPU has its own caching system. So there's no like one accurate way of doing caching anyway. But we're doing what's called direct mapped. Direct mapped, which means no set associativity. And then we've got L1, which has 10 cache lines, L2, which has 100 cache lines, L3, which has 1,000 cache lines, and then you've got RAM. Okay. And what were the costs that I used for L1, L2, and L3 was like 4 cycles? 20? 75? Something like that. And then RAM, like 200. So RAM is effectively infinite for our program here. For 10, 75, and then 200. Okay. Can I click? Can I click? Can I click? No, not letting me click. No. select pins now. Good job on that. I can't draw anymore. And it's not like Microsoft is a company of experienced computer science people, right? There you go. Thank you. Jeez. Yeah, I mean, I clicked on that. I don't know. Okay. All right. 4, 10, 75, and 200. Okay. So, when you load a memory address, normally when you load a memory address, you care what's stored in the memory address. Before these cache exercise things, we don't care. So let's say we do load for memory address 42, and then we do a load for memory address 420, and then we do a load for memory address 52, and then a load for memory address 42. Okay, so given this is our cache hierarchy, which again, highly oversimplified, but whatever. In reality, they're not powers of 10, right? I just do that to make the modulus easier on you guys. Okay, so which slot is 42 going to go into? So our L1 has 10 slots. Our L1 cache. 6, 7, 8, 10, 10. Okay. So our L1 cache has 10 slots. So when we do a LDR42, is it in cache? When we start off, cache is empty, right? This is could be a cache hit or a cache miss. What do you guys think? If it's a cache hit, which level of cache is it hitting? Well, our program's never loaded memory address 42 before. So it's going to be a cache miss. And so it's going to write 42 into here. And so that's going to be cache miss, cache miss, cache miss. We've never seen these things before. So that's going to be 200 cycles for this one, 200 cycles for this one, 200 cycles for that one. But now we're loading somebody that we've loaded before. And we need to find out if he's still an L1 cache, or if he's an L2 cache, or if he's an L3 cache. So this guy's going to go into slot 2. This guy's going to go into slot 0. This guy's going to go into slot 2. So this guy is going to get knocked out of... I'm going to make these a little bigger here. This guy is going to get knocked out of slot 2. I guess I don't need to draw the rest of them. So 420 is in here, and this guy is going to be 52 now. So after the third line runs, this is going to knock out 42 from slot 2. Then the L2 cache, which is much, much bigger. We've got slot 42, slot 52, and slot 20. So in slot 20, we've got 420. In slot 42, we've got 42, and slot 52, we've got 52. Okay. And so when we do a load of 42 here, then what's going to happen is it's going to see if 42 is in L1. It's not. So it's an L1 cache miss. Then it sees if 42 is in L2 cache, and it is. So this is a L2 cache hit. And so this one is going to be 10 cycles. Okay. And so all told, the cost of this program is going to be 610 cycles. Okay. Because we've got cache miss, cache miss, cache miss, and we've got an L2 cache hit. Okay. Do you guys want to do one more example of those? Or do you guys feel pretty comfortable with caching? All right. So I'll start off this time with a store. So I'm going to store 6152. I'm then going to load 42. Then I'm going to load 252. And then I'm going to load 6152. All right. So let's see what's happening here. And I'm probably going to need to draw L3 cache at this point. Okay, so store 6152. Is this a cache hit or a cache miss? When you do a store, is it a cache hit or a cache miss? A little confused whenever you load from RAM, and if it hits at which level of cache would it be stored? It gets stored at all three levels. It gets stored at all three levels. Every time you do a cache operation in the memory subsystem we have here, it goes into L1 and L2 and L3. Okay. So store is an automatic hit because all the CPU needs to do is talk to L1 and be like, here you go. And so that is going to store 6152 into L1 and 6152 into L2. Let's move it a little bit further down. 6152, slot 52, and then in slot 152, 6152. I'm not going to draw all 1,000 slots here. Yeah. Store is always an automatic hit. Yeah, how could it miss? Right. It just all the CPU does, it talks to the L1 cache. You go, here, store this, and then L1 can store it, and then you can think of it as the L1 cache then passes it on to L2 cache, which then passes it on to L3 cache, which then passes it on to RAM. You can think of it that way. Okay. So we're going to load 42. So when we do 42, so this is a cache hit, L1 cache hit, right? L1. So, are you doing this to me again? Really? All right, so this is a L1 cache hit. This one, loading 42, cache hit, cache miss. Yeah, this is a cold start cache miss. So that's going to go to RAM. That is a cache miss, however you want to put it. So let's see, this one is 4 cycles in cost. This one's 200. This guy's also a cold start cache miss. It's RAM. That's 200. Okay, so let's see. Let's update our caches based on this. Come on. There we go. Thank you. Okay, so when we load 42, what's going to happen is 42 is going to go into slot 2. 42 is going to go into slot 42 because 42 modulus 100 is 42. And it's going to go into slot 42 and L3 as well. And then if we load 252, that's also a cache miss, RAM hit, however you want to put it. And so 252 is going to load into slot 252 because 252 modulus 1000 is 252. 252 modulus 100 is 52, so it's going to erase this guy 6152 out of slot 52. This guy is now going to be 252. And then it's going to erase 42 out of slot 2. And so now, this is what the cache is going to look like when we do this one. So when we do 6152, it's going to check L1 cache. Nope, not there. It's going to check L2 cache. Nope, not there. It's going to check L3 cache. Wait, wrong one. Yes, it's there. Okay, so this is an L3 cache hit. And we'll say the cost for that is 75. And then afterwards, is it doing it again? Are you doing it? Are you doing it again? Such garbage. Like, it's accepting the double click, but it's not taking the single click. So weird. And then after we do the load 6152, then this one has been updated and this one has been updated. The caches, all 3 caches update every time you do a load or a store. Okay? So this one now has 6152. This one now has 6152. Every time you do a load or a store, all 3 of the caches update. Okay. So let's do one more. Load 42. What is this? So if I do a load 42, is that an L1 hit, L2 hit, L3 hit? Which one? Good. Yeah. So every time you do any load, any store, it updates all of the caches. It's the important thing you need to get into your head. So this is an L2 hit that costs 10. And so after the load 42 takes place here, come on, eraser, thank you. Then it'll look like this instead. And this guy, 6152, is still an L2, still an L3. But because both of these guys are having contention over slot 2, if you keep loading 6152 and 42 back and forth, they're going to keep erasing each other out of L1 cache. And that's why, in reality, we have something called set associativity, where if it just so happens that 2 memory addresses just keep hashing to the same bucket, then there's actually room within the bucket for both of them to coexist peacefully. And so there's 4-way set associative and 8-way set associative. So if there's like 8-way set associative, then each bucket would remember the 8 most recently or most frequently, depending, used memory things. And so you could have both 62 and 50, 61, 52 living in the same bucket. But that becomes very annoying to do in your head, right? So I do the simplest system that I can think of for you guys. So the total cost of this program here would be $489. So. How does that change performance? Well, when the thing about direct mapped caching is that it's easy to do in hardware, right? So you can have cheaper hardware, and a lot of times cheaper hardware can be faster as well. But the thing is, like, let's say you're averaging a big array together, and if the memory access pattern is such that things keep mapping to the same cache line, then then rather than getting a bunch of L1 hits, you get L2 hits instead. And so when you do set associativity, if you just get unlucky and just have cache contention over one line where these, like, you read from X and it erases line 2, cache line 2, you read from Y and that just happens to be the same memory address hashed together. It's also on memory cache line 2. Then every time you read from X, it it throws Y out of cache. Every time you read Y, it throws X out of cache, and your performance of your program is going to decrease dramatically, because rather than every memory access being 4 cycles, it'll be 10 cycles, right? And you have no way of controlling that as a programmer, because it's just X, it's Y, and they just happen to, when you modulus them, land on the same cache line, and so your programs will just occasionally run 2.5 times slower, right? And so when you have set associativity, then random conflicts like that, you have to, like if you have a 4-way set associative cache, then you have to have 5 variables all randomly hitting the same line in cache, which is more rare, right? It's a lot more rare. And I think mine is 8-way, or let me pull it up. But I mean, you obviously get less cache lines, right? So if before we had 10, if we did 2-way set associativity, we'd only have 5 cache buckets, right? Like, it doesn't magically multiply the number of things you can store. What happens, you get less buckets, but those buckets can remember who was most recently used. And so it has the tendency of being harder to implement in hardware, which means more cost, things like that. And maybe slower, it takes longer for the cache to return true or false, right? But on the positive side, when you run a program, if 2 variables are throwing each other out of cache by accident, then it'll be much faster. And so if you're asking which one is better, Shami, the answer is it depends. And so what, like the first head of ACM, Mason Twanta, at our school, the CSI 45 trophy that unfortunately will not be given out this year because of coronavirus. This is the first year that the CSI 45 class will not have a competition where students get their names engraved on a plaque for a perpetual trophy. The first president of the ACM, Mason Twanta, his uncle works at Intel, and he does this. So that's his job. And so basically they come up with a new CPU, and it's like, all right, what set associativity should we use? Right, here are the parameters. If we come up with 6-way set associative, it'll take 5 cycles to access L1 cache, and if it's 4, it'll take 4, and if it's 8, it'll take 7. So they come up with all these parameters of like, this is the options that we have for caching. And then what he does is he simulates it. So basically there's a number of standardized benchmark tools and things like that, and you run the benchmarks on it, and based on the performance of different size caches and set associativity of caches and all these different parameters for the cache hierarchy, he basically runs simulations over all these different combinations of parameters and sees which one will yield the highest performance. So there's no right answer, right? A lot of times it's just a matter of you just try, let's see how fast it'll be if we do this. Let's see how fast it'll be if we do that. And sometimes it might just be a difference in cost, right? And so it's like, all right, if you pay $10 more, you'll get another 1% of performance. That's probably worth it if you're on a high-end, CPU. If you're on an ARM, probably not worth it, right? The cost of the CPU has gone from $5 to $15 for a 1% speed increase. No. Seems like a bad idea. All right, so here is my CPU. So my L1 is 8-way set associative. My L2 is 16-way. And my L3 is 11-way. So interesting, it's not a power of 2. But probably Mason's uncle figured out that 11-way is faster than either 10-way or 12-way or 16-way or 8-way. And so 11-way it is. So what that means is that every bucket, every cache line here can have 11 different entries in the L3 cache. And for the L2 cache, every entry here can have 16 different memory addresses cached in it. And for L1, both for the data and the instruction cache, you can have 8 different memory addresses, values saved in it. Okay. So, any questions about caching? So every time you load something, 64 bytes are loaded for memory. That's also something that is not represented here in my overly simplistic caching model designed to make your lives easier, is that you actually load 64 bytes at a time. So right here we're loading like an integer at a time or something, which is 4 bytes, right? In reality, you're going to be getting 16 integers at a time. And so if you load from one spot in memory, you actually get 16 integers that are contiguous around that spot in memory. And that's really useful when you are doing a for loop, because as you do a for loop, you go down one integer at a time through memory. It's probably already cached the people ahead of it in in the array. And so you would get one cache miss every 64 bytes instead of a cache miss every new integer you load, right? So you'd only get one cache miss every 16 ints instead of a cache miss every int. Do you guys understand how that's way, way faster? Right? Because a cache miss is 200 cycles, right? A cache miss is 200 cycles, and so if you load one int and then you get the next 15 ints in memory, because most of the time when we iterate through, it's not a double word. A double word is 8 bytes, right? So it's going to load 8 double words at a time, or 16 words at a time. And the reason for that is the way that RAM works. RAM's kind of a weird beast that we haven't talked about yet. But it's actually a lot cheaper to do it this way than to load like one word at a time. And so if you're just, if you have a for loop for int I equals 0, I is less than 1,000, I plus plus, and you're just loading, values, and like let's say you're averaging an array, then the first thing you load is going to be a cache miss, which it always will be. The first thing you load is always pretty much a cache miss. But then when you go to array 1, array 2, array 3, array 4, array square bracket 4, array square bracket 5, all of those are in memory already. Cache it, cache it, cache it, cache it, cache it. And then when you get to the end of the 64 byte line, which might not actually be on the 16th integer, because who knows where you are within it. Doesn't really matter. When you get to the 16th integer, then you get another cache miss, 200 cycle penalty, and then you get cache it, cache it, cache it, cache it, cache it, cache it. 16 of those, cache miss, cache it, cache it, cache it. And so rather than getting a cache miss every time, you do a load of something new, because it's very common for us to just go through memory sequentially, you get one cache miss every 16 integers instead of every integer. So would it be 32 bytes per load on a 32-bit system? So here's the thing. Like, we're loading 32 bits. What's happening is the memory subsystem behind the scenes is actually preloading the next 15 integers. Okay? So even though, and you don't have to do this for your worksheet or for the midterm, because it will complicate things, right? Like, you do one load and it does 16 loads, right? And that's the kind of thing that you simulate with a program. And like when I took this class as a junior, we wrote a program that would simulate how caching worked. Because after a while, like your human ability to track these things kind of gets overwhelmed. But the point for you guys is that in reality, you only get one cache miss out of every 16 loads you do. And it's actually better than that on modern systems, because the modern systems can actually have a bit of silicon that looks at what you're doing. It looks at your assembly code and says, oh, he's doing a for loop. How long is that for loop going to run for? 1,000? Okay. And then there's actually, on Intel chips, I don't think on ARM, but on Intel chips, because Intel wants performance. ARM wants simplicity and lower cost and lower power. Intel wants performance. Those are two different designs, philosophies. And so Intel will, modern Intel chips have a thing that will actually look at your assembly code and figure out, okay, you're doing a for loop, and start preloading memory and things like that, which is pretty cool. Kibibyte is a power of 2, kilobyte is a power of 10. Yeah, Kibby Byte is like one of the dumbest names ever. A Kibby Byte. It sounds like a third grader with a speech impediment developed a standard. How many Gibby bytes do you have? How many Mebby bytes? Debbie bytes. So in reality, caching is more complicated than what we're doing in class. That said, all you need to know is the dumbed down, stripped down caching system, because that is enough to kind of develop your intuition for how caching works. Okay? It's crazy that it'd be able to do it. Yeah. It's ridiculous how much thought that AMD and Intel have put into their silicon. And like they're like there's a machine within the machine, right? Like your Intel chip actually runs an operating system inside of it. You don't have access to it, but there's actually an operating system running inside of your chip that does things like well, we'll learn about those kinds of things later. We haven't really had a lecture on RISC versus CISC and that kind of stuff yet. But it's ridiculous how much thought they've put into this, you know. And they're trying to squeeze every last ounce of performance out. And you can see the difference between 4 cycles of delay and 200 cycles of delay is noticeable, right? And so one of the things they try to do is if it's predictable, you know, like if there's a for loop and you're just running through memory, what can we do to never get a never get a cache miss, right? Because it's very predictable behavior. It's very rare that you'd sort of randomly roll a die and grab that element of RAM and randomly roll a die and grab that element of RAM. It's very kind of unusual to do that. I guess you could. You know, the wavelet in encoding and decoding program that I worked on, it did sort of randomize the data transmission, but you know, it's uncommon. Usually we just start at the beginning and go to the end, right? And so CPUs, it's this synergistic relationship, right? Programmers write a program, and then CPU designers write CPUs that will run that program quickly. And then programmers learn how CPUs are made, and they rewrite their programs to squeeze performance out of the CPU, like what you guys have been doing this whole class in assembly, right? Let's try to figure out a way of squeezing more performance out of it. Let's use this trick, and let's use that trick, and let's use this suffix and all this stuff. And then the CPU guys will be like, oh, look, you know, these programmers are doing this. Let's do this to make it faster. And then the programmers go, oh, look, there are these new tricks, and so the programmer, the software and the hardware side build on each other, right? And it's this weird synergistic relationship where like sometimes like you can like people will actually just directly request something. Like, you know, it'd be really cool if there was a hardware instruction that would take a photo, right? Like I want a new assembly instruction that is called photo. All right, photo. I'm gonna request this photo, and I'm gonna give you a memory address, and you're gonna give me a pointer in that memory address that has the photo. It's gonna take a photograph and store into this memory address here the RGB values. And you think I'm joking? This is actually a true story. So if you have, you know, this is not ARM, by the way. You know, ARM does not have a photo command, unfortunately. But yeah, in the past, they were spending a lot of CPU cycles, like doing the adds and the multiplies and all that stuff, to take a photograph. And they eventually just requested from the CPU designers, hey, implement a photo command for us. And they did. But the trouble is, like, once you've added that to your CPU family, then every CPU you make since then has to have the photo command. And so the silicon guys have to be very thoughtful about when you add a new command to something, because you get stuck with that forever. You know, bad decisions are So the CPU guys tend not to do specialized things like that. But yeah, in reality, back in the 1970s, there was a CPU that had a photo assembly instruction, and it'll take a photo for you. And there are other weird ones like open the case, and you would give an assembly instruction, and the side case of the giant mainframe would like open up, you know. And then if you make a new version of the CPU, well, you got to support that. Well, we don't even have cases anymore. Well, it sucks to be you. If that code doesn't run, then all the old code is broken now. Right? They're forever because they keep backwards compatibility. Exactly. Intel tried breaking backwards compatibility with the Itanium system. Itanium. Anyone here have an Itanium system? Anyone? Intel Itanium CPU? Anyone? Nobody? Exactly. So Itanium was. It sounds old. You'd be surprised. It is old at this point, but they were in production for a lot longer than I thought they would, because it was a complete failure. It was a joint production with HP, Hewlett Packard, and the notion was like, let's just do away with backwards compatibility. People can just recompile their code, whatever. So it came out 20 years ago, and it was discontinued. Not yet. It will be discontinued this year. So, this is the last series of Itanium chips. So yeah, so Itanium was a cool computer architecture that did lots of cool things and was an abject failure. And the reason why it was a failure is because it could not run x86. Nope. It's called x86. No. That's the problem. It could not run any program that was compiled for x86. So Intel's like, just recompile your code, bro. You know, they dumped a lot of money into compiler research and coming up with a compiler that would optimize for the Itanium architecture. And yeah, nobody wanted to do that. So basically, if you have an executable that will run on your standard PC, it would not run on Itanium. You would have to get the developer to recompile it. And what happens is that, yeah, people don't do that. People want to just be able to go like, I need WinRAR, you know, and they'll just... I need WinRAR on my computer. And then they go over here to 32-bit English, which is x86, right? And you'll see we get a .exe file. Okay, the .exe here is going to be an x86 format. Okay, this is basically object code for x86 assembly, essentially for x86. This will not run on Itanium. Okay, if Richard Stallman's vision of a world in which the source code for everything is available, if you purchase WinRAR, comes with the source code, then people would be able to compile it themselves for Itanium, and it wouldn't have been an issue, and probably would have been a success. But the unfortunate direction the software industry has gone is that most people don't share their source code, for better or worse, and mostly for the worse. So because people don't share their source code and they only release x86 executables, and nowadays, like you saw, there's a 64-bit version, right? So this doesn't run, the 64-bit either. And Itanium was a failure. And so we're stuck, we're stuck with using these CPUs that still support bad decisions, right? Like technically, you could probably take assembly code for the have you guys ever heard of the Intel 8088? You have to buy WinRAR. Nobody's ever bought WinRAR, dude, I don't think. the Intel 8088. Isn't there like the roll-in? What was that? 808. Yeah. No, the 8088 came out in 1979. So that is sort of the first real. There was the 4044, I think, before that, which I don't think necessarily qualifies as a real CPU. But this is kind of like Intel's first CPU, first general purpose CPU that really caught on. The 4044. Let's see. Yeah, it doesn't matter. The 8088 was really the first one, and the 8086. Yeah, so the original IBM PC is based on the 8088, right? And so the original IBM PC is the OG machine that all of your PCs have descended from, unless you're a Mac person. The IBM PC, the IBM personal computer, the name of it, 5150, that's hilarious. Yeah, a 5150 is when you do an involuntary psychiatric hold. That's amazing. That's the model number. Okay. Like if you go over here, you'll see where it says this PC, right? It's called a PC because of the IBM personal computer. Right? That's why it's called a PC. This is the OG, in modern terms, $4,000 for this thing. Right? Came out with the Intel 8088 running at 4.7 megahertz, not gigahertz, megahertz. 16 kilobytes to 640 kilobytes of RAM. There's the famous quote by Bill Gates that 640 kilobytes of RAM is enough for anyone. Comes with a PC speaker, which is the... You can get music out of it, kind of. It's kind of really super garbage. You see San Diego right there representing. So UCSD developed an operating system called the P system. And Pascal was a programming language, still is technically, and it was actually quite successful. And what was really funny was that UCSD did not want to be. This is my alma mater, like my computer science department, and they didn't want to be in the business of selling operating systems, and so Microsoft ended up taking over the world. But it would have been a very different world if UC San Diego had been more aggressive in pushing the UCSD P system. I wonder if I know any of the people that made it. Who are the people that made it? Nope. Nope, none of those guys were there when I was there. That's unfortunate. And so basically, they spun it off to a third-party company. But anyway, so the original Microsoft operating system was MS-DOS, and so back in the day, the winning combination. There's also CP/M. CP/M gave Microsoft a run for the money. And so there were you actually could run on your IBM personal computer different operating systems, and the combination that won was the IBM PC plus Microsoft DOS, MS-DOS, and that combination became, because it was more popular than the others, people started writing code for that combination and not for any of the other ones. And so what happened was people wouldn't stop using the other ones because, I want to play, King's Quest or whatever. And so basically, once one combination gets sort of a competitive advantage, then everybody migrates to it, and then people stop supporting the other ones, and then it becomes like 100% or close enough to it. So yeah, so the combination was Intel CPU, Intel 8088, IBM making the computer, and Microsoft making the operating system. That was the winning combination that took over the world. And it didn't have to be that way. Like I said, UCSD could have, beaten Microsoft, and my department could have been the, I don't know. We could have had like a spaceship as our building. You get into UCSD computer science and you like get a trip to Mars or something. I don't know. Can you imagine like how much money? Instead, we had this really sad AP, and we had this really sad building when I was there. It's like it's just all concrete and very gloomy. The applied physics and mathematics building, and computer science was just based out of this building because I don't know. So yeah, anyhow, so the 8088 was the original, Intel CPU really, and there's other ones as well, the 8086 and other ones. The Intel originally made a CPU for a graphing calculator actually. So Intel came about with the idea of a general purpose CPU for making like a calculator basically. It's like when you guys start off with simple calculator in CSI 40, like it's a time-honored tradition. And so what happened was Intel then came out with a 186. And the 186 had to be backwards compatible with the 8088 because people had published a lot of things that ran on the 8088. And so if the 186 didn't support all that stuff, people wouldn't buy it because this had, let's say it has like 90% market share. And if you come out with something that doesn't support with backwards compatibility of the thing that has 90% market share, as Intel shows us, or Itanium shows us, people don't buy it, right? And so then what happens is people start buying 186s and they can run all their stuff. And then eventually the 186 gets 90% market share, and then they release the 286, and the 286 has to be backwards compatible with the 186. And so they add things to it, but they don't take things out of it. You guys understand? So like when they come out with a new standard, they can add new things, like they add new assembly instructions and things like that to the 286, but they don't remove things. And so, come on, one note, there you go. And then eventually the 286 takes over market dominance, but then Intel's like, guess what, guys, it's time for the 386. And then that one takes over. And then, do you guys know what's next? Do you know what's next? Intel was very, very creative with their naming scheme. You know what's next after the 386? 386 would have been late 80s to early 90s. 286 would have been mid 80s, 186 early 80s, if I'm remembering that right. Maybe Intel 386, maybe 1990, I'm gonna guess. It's a long time ago. Damn, 85. Okay. 85. And then, let's see, the 286. Nah, doesn't matter. Anyway, so this was during the 80s that Intel went from one to the next to the next. And each time it's backwards compatible. So on a 386, you could run 8088 code. And so if you had some legacy code from the late 70s, the 386 could run it. And then after the 386 takes over, then Dolly is the only person who got it. It is the 486. Yes, the 486. And the 486 early 90s. '89. Okay. Then after the 486 came the what? Why are they obsessed with the number 86? Because the original, Intel was the 8086. And so this was the 086, then it was the 186 and the 286, so on and so forth. So they use that number to indicate the generation, basically. But the trouble is you can't copyright a number. And so what happened was Cyrix and AMD came out with 486 clones. You'd have the AMD 486 because you can't copyright a number, you can't trademark a number. And so with 486, after 486 was the Pentium. And so if you ever wondered why we have Pentiums, it's because you could trademark. You can't, and so AMD came out with a 586, and Intel came out with the Pentium, because Pentium could be trademarked, 586 cannot. And Pent, of course, means 5, right? Is that why it's called x86? Because it's compatible with x8? Yeah, so x is, like a variable, right? So x86, there's 386, 486, 586, 286, 186, 808. Yeah, and so x86 is that whole family of CPUs. It refers to that family of CPUs. And so when you learn x86 assembly, you're learning the shared assembly language that runs through all these generations. Okay? And so some commands will be like, this command first appeared in 386. And so they have different versions of x86 assembly. Right? The core language is the same. You could, run essentially 8088 code on your modern CPU. It would run fine. Okay. Most of it, it's backwards compatible, right? And so, after the Pentium, you had what? Pentium Pro. What came after the Pentium? Pentium 2, yeah. So there was the Pentium Pro. There was the Pentium 2. AMD started its own naming system, and we're getting into like trivia territory there. And they came out with like a number of CPUs that I bought. The number I didn't buy, because by the time they got to like Bulldozer, like AMD was getting its lunch, you didn't buy Intel. Anyhow, so eventually we came to the modern days where we have like the Pentium Core series, and you have the Core i3, the Core i5, the Core i7, and they also have like the Atom series, which is a bunch of crappy CPUs. And so then they did, from Pentium Core, there's generation 1, 2, 3, right? And so that's how they've been numbering the generations, right? So I have a generation 7 i7, or actually there's an i9 there, right? So I have a generation 7 i9. Okay, and they're going to be coming out with like generation 11. What is it? Rocket League. They have code names for each of their generations. Yeah, so 11th generation core. It's coming out soon. Okay. 14 nanometers. Poor Intel. Poor Intel. TSMC is down to like 5 nanometers now, and yeah. Intel's been stuck for a while now, and so they've been squeezing better efficiencies out of their CPUs, but man, it's just not been a good couple years for Intel. So IPC is kind of an important concept. So IPC means instructions per clock, and so there's two things that matter when it comes to, I guess we're learning new things now. There's two things that matter when it comes to CPU speed. So CPU, you doing me like this again? All right, no. Thank you. So CPU power like CPU speed, CPU, I didn't say power, how fast it is based on two things. It's based on the clock rate times instructions per clock. Okay, so let's say your clock speed is 2 gigahertz, 3 gigahertz, 4 gigahertz, say 4 gigahertz, whatever. So let's say your CPU does 4 billion cycles per second. So every second you have a little, piece of quartz or something in there that generates a signal that goes up and down, up and down, up and down, up and down, 4 billion times per second. And let's say that your CPU runs 1 instruction per cycle. Then you're now running 4 billion instructions per second. But in reality, this is not 1. Like everything that we've talked about in this class so far would indicate to you guys that this number is 1. Every cycle you do 1 instruction. With some exceptions like multiplies and things like that. But that's a simplification. And I deliberately oversimplify things for you guys because it's overwhelming if you get hit with all of it at once. And so the naive assumption is IPC is 1, right? In reality, there's a lot of things, and that's what we're going to be learning about the next couple weeks, is the number of ways you can boost the instructions per cycle and get that number as high as possible. Okay, and so what happened was, even though their clock speed, actually 5.3 gigahertz is not bad. That's actually pretty damn good, really. That's the big reason to upgrade, I guess. And also, I think it's got USB 3.2, 20, it's not very good. PCI Express 4, right? So Intel's been sort of potatoing on PCI Express 4 support as well. Intel's, really, AMD has just been cleaning Intel's clock recently. They have just been not having a good couple of years. When I first started teaching this class, the students were like, should I buy AMD or Intel? And I'm like, Intel's better. And now AMD is just completely, kicking Intel's ass. So, yeah. So AMD came out with PCI Express 4 support like a year ago or so. They're not going to have this until the next generation. You hate the new USB naming scheme. Yeah. There's some issues there as well, for sure. Now that AMD is winning, they're able to jack up their prices. That's actually an interesting question, because there's a global silicon shortage right now, right? And so there is just not enough production foundries. Foundries are one of the most, if not the most expensive building to build on Earth. You think it's a skyscraper. No. The most expensive building to build on Earth is a foundry, a semiconductor foundry. Because the way that it works is when you make a CPU chip, you start with like a block of silicon, like a big ingot of silicon. And you refine it, you spin it, you end up with these things called silicon wafers. And so they look kind of cool. And there's bigger wafers and smaller wafers. And what you do is you have a wafer, and then the foundry is done in a ultra pure environment. The reason for that is you've got these lasers. Right now we're up to extreme ultraviolet lasers, very, very narrow wavelengths, right? Because the smaller the wavelength of the light you use on the wafers, the smaller the features you can make, so you can pack more and more transistors into the same size. That's what earlier we had, like the 14 nanometer that Intel's on, and TSMC is down to 5 nanometers. That means TSMC can draw something that is 5 nanometers wide, whereas Intel is almost 3 times as big. So TSMC can pack things like, in the same area, you can get 9 times as much stuff in it. And so what happens though, what if there was a piece of dust, and the piece of dust lands on the silicon wafer and the laser shoots it? is that it breaks, right? That the CPU may or may not be functional. And so foundries are in this ultra pure environment. Like ridiculous amounts of effort are spent to completely homogenize the manufacturing experience. Intel does things like testing the humidity in the air, and they try to they reproduce everything like down to the centimeter. Everything in an Intel foundry is reproduced at another foundry to get consistency of manufacturing results. It's ridiculous just how much detail they put in these things. And so you can see here you've got a bigger wafer and it's making bigger chips, and basically the bigger your chip is, the more likely it is that a piece of dust lands on it, right? And if the piece of dust lands on something critical, it blocks the laser scatters or whatever, it doesn't matter. At that point, that CPU is toast. And so the bigger and bigger the CPUs you make, the lower the yield rate. The yield rate is what percentage of CPUs that come out of this thing actually work. Okay? And so a lot of money is put into raising the yield rate. And, for some manufacturing processes, the yield rates might be 10%. So 1 out of every 10 CPUs that come out of this very expensive process actually work. And so you have to charge 10 times as much, right, to make up the difference, right? And so that's why smaller CPUs are cheaper, right? Because you can A, make more of them, and B, they're less likely to have a defect on them. When a piece of dust lands on one of them, it takes out that one, but the other 9 work. And that's why you get this exponential cost for the top end stuff. The 3090, let's see, what's CPU, Ampere, TSMC 7 nanometer, right? So the feature size is 7 nanometers. And they're starting to go 3D, so it's not exactly apples to apples comparison. Intel does it slightly different from TSMC, but they're doing FinFETs, which kind of come up off the board. PCI Express 4 if your CPU supports it. How big are you? How big are you? Doesn't say. Anyway, the GPU, the Ampere GPU chips are gigantic, absolutely gigantic. Does it say on here? Thank you, sir. Die size 628 millimeters. Okay, millimeters squared. Sorry. So it's 600 millimeters squared. Cool. Now let's look at how big the Raspberry Pi system on a chip is. And so for the Raspberry Pi has a complete system on a chip, which means it's got RAM and the CPU and other things all integrated into one tiny, tiny little chip. It's one of the best-selling British computers. More than 30 million. Cool. Processor. Broadcom. That's the old one, the 2835. This one, BCM 2711. Okay. The 2080 Ti was 754 millimeters squared, but it was on a cheaper process. Any update on the Raspberry Pi distribution? No, not yet. Might not happen this semester. Data sheet. Caches. I know. Yeah, the pandemic sucks. But the school doesn't seem interested in distributing it. So if I did it, I'd have to do it myself. Let's see. No, it doesn't have the information on it. No. Anyhow, the point is that the Raspberry Pi, if somebody could look that up, how big the BCM 2711 is, I'll post that into Discord. But it's way smaller, and so the kicker is that kicker is that this wafer is expensive to make, expensive to manufacture, and if you can fit 10 times as many CPUs on the same wafer, and your yield rate will go up if you can make it smaller, right? Because there's less likely for dust to land on it. Then let's say that you could either get 10 CPUs of which one works, or you can get 100 CPUs of which 99 work. It's 99 times cheaper, right? And that's why high-end chips are so damn expensive. And so on top of this, there is a shortage in the world of semiconductor manufacturing capacity. The Intel has been trying for years to do the next die shrink, the node shrink, where they're going from 14 nanometers to 10 to 7 to 5, and TSMC has been able to do it. Intel is not. And so Intel is actually thinking about using TSMC, the Taiwan Semiconductor Manufacturing Corporation, to make their CPUs, which would be a huge disaster for Intel, honestly, because they're one of the world's biggest, semiconductor manufacturers, and they're basically like, we can't figure this out, or we can. It's just taking forever. The top flat area of the BCM 2711 is 10 million or 100 millimeters squared. Yeah, so the 2080 Ti I have in my system here is 7.5 times bigger, right? And so that means the yield rate is going to be a lot lower, and also you can fit more Raspberry Pis onto one wafer than you can Turing or Ampere chips. Okay. And so they will use TSMC for some stuff. Yeah, it's just really not good for Intel. A friend of mine actually went up there to Oregon, where they have a lot of their manufacturing stuff, because he works with EUV lithography and stuff like that, and their company is a dumpster fire right now. That's all I can tell you. It's just not a good situation. So yeah, and so that's how manufacturing kind of works. You basically get a wafer, you put a photoresist on it, which is like, if you guys ever know how like developing film works. So basically you put a photoresist on it, then you hit it with laser light, it develops the film where the laser light hits, you do an acid wash that washes away the stuff that wasn't developed, and that will etch wires essentially into the silicon. And the way the silicon works, it's a semiconductor, so even though it's all silicon, you can have parts of it that work like wires, and you can build transistors onto it by doping. You have a P and an N region, and by putting a P and an N and a P together, you get a transistor out of it. And two transistors, as we learned in CSI 26, can be used to make logic gates, and transistors can be used to make RAM. And yeah, and so basically through that process of just kind of like using a laser to draw lines on a piece of silicon and selectively doping it, then you can basically get RAM and CPUs and everything else we know and love. But the trouble is there's just not enough manufacturing capacity right now. It's a really weird situation. Like I don't think there's been a period of time where something like this has happened. Maybe with a RAM market, there were some floods in Thailand, I think, that wiped out a lot of the world's RAM manufacturing supply, and RAM prices skyrocketed. But like right now, like Ford has had to halt production of Ford Fusions because they can't get enough CPU chips to put into the cars. And so our world is like designed to have a very shallow inventory system. Like we do, like there's a couple different terms for it, but basically the notion is don't maintain inventory. Inventory costs money, right? And so what happens is that the manufacturer will manufacture something and hand it to the automobile person, who immediately puts it into a car. And so as long as that supply chain is all working, then you don't have inventory, which costs you money. But now they're suffering from that because they ran through all of their stock, and there's not enough capacity to keep up with demand. And so TSMC announced that it's actually going to be prioritizing automobile chips over other stuff, because like the world's automotive industry is hurting right now because they can't get enough chips. And we haven't been able to find anyone that has 3090s in stock, right? If you go to Newegg, the 30 series of NVIDIAs came out half a year ago at this point, something like that. And components, video cards, desktop graphics, GeForce 30 series, sold by Newegg. They used to have an option for in stock. That is not a 30 series. Okay. Show some PC some love. Out of stock, 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 out of stock. Look at all these different manufacturers, right? All of them are out of stock, right? And so this is a you know, you can blame the pandemic, I guess, but it's not really a pandemic issue. There's just not enough manufacturing capacity, and you'd be like, well, why don't they build new foundries? And the answer is because they're bloody expensive, you know, and they are. That is the other answer, right? Literally everything is out of stock everywhere you go. So yeah, if you buy a pre-built PC because they have their own supply chains, right, then you can get a 30 series with it. But yeah, it's just kind of ridiculous. It's like Intel was never that competitive. AMD just sucked a whole lot. No, I mean Intel in the Ivy Bridge and Sandy Bridge era, which was the second generation of the Core series. Intel did some pretty innovative stuff, right? So Ivy Bridge is third, Sandy Bridge was second, I think. Let's see, second generation, yeah. So Sandy Bridge was on 32 nanometer process. Came out 10 years ago. And you know, honestly, the if you used an Ivy Bridge or a Sandy Bridge CPU today, you wouldn't notice any difference. And I know that because I had one for a long time. I had a Sandy Bridge for 7 years, and then I upgraded to this Core i9 that I have, and it didn't make any difference. It made it a bit difference because I like, for peripherals, you know, like I was able to get a faster SSD and things like that, the NVMe SSD, but in terms of like video games and things like that, it's not noticeable. And so yeah, around the time Sandy Bridge came out was when Intel really started just chewing up AMD. Like, there was no reason to buy an AMD during that whole time period. But then Intel's been sucking since then. Okay, so whenever you're talking about the hardware stuff, there's really two things that govern performance. One is the clock rate, how many clocks a second the CPU can go up and down, and the other is IPC. And so for a long time, the time to buy a $100,000 PC card, yeah, I was actually looking at that. You're talking like $4,000 or $5,000 to get a 3090. You might as well just go with a scalper at that point. Although I refuse to give money to a scalper. So for a long time, the clock rate was the thing that was driving performance. There's a concept in architecture called Moore's Law, right? And so a lot of people took this to mean the speed of a CPU doubles every 18 months. It's not really a law, it was just an observation he made, and it actually held true for about, I don't know, 30 years or so. It's broken now. Like, we have not been able to keep up with Moore's Law because exponential growth is difficult to do. You know, the fact that it held up for 30 years is really impressive. The way that he actually phrased it was the density of transistors. He was talking about how many transistors you can pack onto a CPU seems to double every roughly 18 months. But people more colloquially would say the speed of a CPU, because that was like how much, you know, how many additions you can do a second. And so a lot of it was actually driven by the clock rate going up, actually. And so you go from 100 megahertz to 150 megahertz to 300 megahertz. Yeah, I can't even draw. But like my, you know, my processors that I personally own, I went from a 60 megahertz CPU to a 100 megahertz CPU the next year, and the next year after that I went up to a 150 megahertz, which I could overclock to 300 megahertz, and that was a $90 CPU, which was amazing. that you could just double the clock rate on it out of the box. And so after that, Intel stopped allowing people to overclock quite so easily, because nobody bought their expensive stuff. People bought the 151, just overclocked it to 300. It wasn't density or speed, only total transistor count. Yeah, that was the original observation. But like I said, the colloquial way that people express Moore's law, because again, it's not a real law, it could be whatever you want it to be, is that the speed of a CPU would double. And that's what you saw with like the clock rates and things like that. And that's why I mentioned it that way, was because the doubling of clock rates was actually what drove the industry forward. What would happen is that the industry would say, okay, what is our current clock rate? And then they'll do some math and be like, okay, well, it needs to be here by next year. And it needs to be here by next year. And so Moore's law was more than, in practice, it was more than just transistor counts. It was clock rate and transistor counts. And this drove this massive growth in CPU performance from the 1970s to about 2010. And in about 2010, it stopped. And CPU speeds were, 4 gigahertz in like 2012. And nowadays, I guess it's up to like 5 gigahertz, 10 years later. It's pathetic, right? So, and the reason for that is speed of light, right? So do you guys know how far the speed of light travels in a nanosecond? What's the speed of light, c? Yes. So what is c divided by a billion? Anyone know? How far, if you have a 1 gigahertz CPU, how far does light travel during that one cycle? Clock goes high, clock goes low, a billionth of a second is taking place. How far does light travel? It travels a foot. Very, very close to exactly a foot. And Grace Hopper, one of my personal heroes, she was this crusty old woman, at the time I was alive. She was an admiral in the Navy. Really considered one of the great characters in computer science. She would hand out nanoseconds to people. And a nanosecond is very, very close to exactly a foot, which makes the foot a better measurement unit than a meter. Right? Like, I think they ought to just have redefined a foot to be a nanosecond, a light nanosecond. And then that would make the, what is C? It's a billion feet per second. Easy, right? Then you would not need to have a different SI unit. You could just have C and time, and you're good. Distance would be defined in terms of a billionths of seconds. They redefined a meter as a unit of C over a unit of time. Yeah, but it's not an even division, right? It's 3.8 or whatever. Anyway, so the point is that if you have a 5 gigahertz CPU, light travels a fifth of a foot. So 2 and a fraction inches, right? Thanks, Imperial System, right? So it travels 5/12 inches, 2.4 inches. So if you have a 5 gigahertz CPU, the maximum distance that light can travel is about that far, right? And so if you've ever seen a CPU, like, they're pretty close to that size, And in reality, what happens, you got wires on the inside that actually add to the surface area of it, and light also doesn't travel at the speed of light through silicon. And so you actually have these issues with, like, the speed of light is providing a fundamental limitation on how fast you can drive your CPUs. Meter was originally defined as 1/10 of the distance from the equator to the North Pole. How stupid is that? It's such a dumb system. It should just be a billionth of yeah. And so if you have a 4 gigahertz system, you can travel 3 inches. And if you have a 5 gigahertz system, you can travel 2.5. And so as CPUs have been getting, like, big, and the clock rate's been going up, is that you actually run into these very fundamental limitations in the speed of light. And so what people have been doing is adding to the instructions per cycle instead. So for years, we were boosting the clock rate, boosting the clock rate, boosting the clock rate. And then Einstein came up and went, stop. Right? Can't go any faster than that. And so ever since 2010 or so, almost all the research has been on boosting IPC. Okay? So if you look at how, like, a GPU does it, the GPU will have lots of parallelism. Okay, and so that's a whole topic we're gonna get into, which is parallelism. So a 3090 CPU isn't fast. GPU isn't fast because it runs one instruction really quickly. It's because it's got all of these different processors all running at the same time, each taking on different chunks of the scene that's going to be rendered on the screen, and they do it in parallel. Okay, and so this is the approach the industry has taken over the past decade. Okay. Let's go back to furlongs. I know light furlongs. Define a furlong in terms of the speed of light. Okay, so that was our architecture talk for today. Let's just review bit operations real fast. So if I have 1011 and I AND this with 0101, what you do when you do a bitwise AND is you just look at each pair of bits, and true and false is false, false and true is false, true and false is false, true and true is true. Okay, so you have to know bitwise AND 1011, 1010, bitwise OR. Again, you just look at each pair. True OR with true is true. False OR with false is false. True, true. So that's OR. XOR. XOR is you can think of each true here flipping the bit above it and every 0 leaving it alone, or you just say one or the other is true but not both. And so if they're both true, the answer is false. If they're both false, the answer is false. Both true, the answer is false. One or the other is true but not both, the answer is true. So AND, OR, XOR, and then you've got NOT, which is a tilde. And that's a unary operator, it's not a binary operator. Binary operators take 2 operands, a unary operator takes 1, and so that would just be 101, 0100. So you just flip all the bits. 1 light furlong is 0.00000671 seconds. Fantastic. That should be our new standard. Okay. Yeah, honestly, like people that like get all like super like snobbish about the metric system, it's like there's absolutely no reason the meter needs to be defined in terms of the equator to the North Pole. Like that's as dumb and arbitrary as anything. You could have a kilofoot if you wanted, you know what I mean? And the foot is actually a billionth of a second. Like it's actually, you know, pretty damn good as a SI unit. And you could just have a decifoot, a megafoot. A megafoot sounds pretty cool too, honestly. A gigafoot. I'm gonna kick you with my gigafoot. Megalight furlong replacing the second. Yeah. Okay. So the worksheet will give you more practice doing this kind of stuff, and there will be some of these on the midterm. But that's I don't know how to make it any harder than this. It's all pretty easy. Now you're sounding like a machinist. Start speaking in thous. We can talk about thou and thee. It's the informal second person possessive thou. We don't use informal. We're all formal now. We use your. The Earth isn't even a perfect sphere. Yeah. Oh, thousandths of an inch. Nice. Kerr metric time. Do you guys have any questions about bitwise operations? This is it, and or XOR not. I don't know how to make it any harder. You have decimal time. Yeah, people have proposed decimal time before. The trouble is like Babylonian, because the Babylonians were like really into like 60s and things like that. Like 60 is actually a really nice number to work with because it's highly divisible. right? You can divide 60 by 1, 2, 3, 4, 5, 6, not 7, not 8, not 9, 10, 12, 15, right? 60 is one of the most highly divisible numbers ever. So if you need to do fractions, you know, like what's a half hour when you have decimal time, right? 50, okay. It's a quarter hour, 25, right? You know, you start dividing any more than that, you start getting into decimals, you know. So the Babylonian system is designed around fractions, right? I'll be there in a Kermit. It's funny. So, any questions about bitwise operations? Let's look at the worksheet, maybe. So here's the assembly to do different things: shifting, rotating. Right. So basically, what you're going to do is you're going to get these assembly commands and write down the value of register 0 after the command runs. Right. So you AND it with 31, AND it with 3, AND it with 1, AND it with 255, and then it will. I filled in some of these for you guys. So you can double check your work. ANDing 0 with 42 is also going to be 0. Nodding things. XOR. Oh, BitClear. Yeah. I did use BitClear in one of our assignments. Do you know when the cache worksheet will be graded? I'm going to try and get to that today. So you guys will know if you did it right before the midterm. I probably should have graded over the weekend, but I just really wanted to enjoy my weekend. Do I have RTX voice on? I do not. Why? Does it sound bad? Is there background noise? RTX voice is incompatible with Wallpaper Engine of all things, so I got rid of it. I do have noise cancellation on in Discord. I turned on noise suppression, so maybe that caused it to sound different. Okay. Yeah, no, really. Like RTX voice, it's a known incompatibility with Wallpaper Engine. Like that's like some Microsoft DOS level of incompatibility where your mouse was incompatible with your sound card, which was incompatible with your game, you know? It's ridiculous. Gotta go, get ready for work. All right, see you. Okay, so BitClear is BitClear is interesting. So what you do with BitClear is it actually clears whatever bits you pass in. And so if you had 000, 11, 000, and you bit cleared 8, 8 is this, right? That's 8. 1000 is 8. And so what happens if you bit clear 8, it turns into 000, 1, 000. So it clears whatever bits are set in the third parameter here. Okay. And if we OR in 3, 3 is the bottom 2 bits, right? So that's all you're going to do for this assignment. And then we're going to bit clear 24. So 1, 2, 4, 8, 16. So 16 and 4 and 2 get cleared. Yep. So when you do a bit clear with 24, that clears the 16-bit, the 4-bit, and the 2-bit, right? No. 8. 16 and 8, sorry. 16 and 8, yeah. So it's going to clear the 16-bit and the 8-bit. So these 2 bits get cleared. If it's already cleared, it stays cleared. Okay. So that is bit clear. So it just erases, sets to 0, whichever bits you pass in the third one. Can you explain bit clear again? Yes. So if you bit clear, like if R0 is 10101010, you did a bit clear of 15, the bits corresponding to 15 are 1, 8, 4, 2, 1. So 1, 1, 1, 1. And so the bottom 4 bits get cleared. So that would turn into that. Okay. So whatever parameter you pass in for the third parameter, those bits get set to 0. Okay. And so this was actually used. I actually used that on one of the homework assignments I did to get some extra performance out of it. It's a nice optimization. You don't need to do it. You can do it with a and a not, I believe. It takes 2 cycles with a bit clear. You can do it in 1 cycle. Okay. All right, so we got 10 minutes left. Yeah, and so the upshot of all this is that you know, if you make a bad decision, right, and if you made a bad decision back in let's say the 186 days, then you've got to support that bad decision for the rest of your architecture's lifespan, which so far Intel is like what 40 years in, 40 plus years in on the x86 architecture. And so a lot of manufacturers over the years have made bad decisions for like a short-term gain in speed, and then they get stuck with it. So like if I learned Spark assembly, and in Spark assembly, you guys are gonna like this, I think. This is in Spark assembly. I'm doing it in, I'm doing an ARM32 because you guys don't know Spark assembly, but I want to demonstrate the point. So in Spark assembly, if you do a branch instruction like this, this command also runs. Yeah. So every time you do a branch, it's pretty common to just put a no op after it, because whenever you do a branch, it always runs the line after the branch, and then it jumps down to Bob. And so they did that because they found that every time they did a branch on one of their early CPUs, there would be a single cycle that was wasted. And so they're like, we'll just make it so that it runs whatever commands after it, and we won't waste that, and we'll get like a 25% speed increase in tight loops and things like that. And what happened though was that if you write the assembly by hand and you forget about that, it will run very unexpectedly. It will run commands you did not expect. And so what you have to do when you're writing it now is every time you have a branch, you have to, is it doing it to me again? Doing it? Yep. All right. Nope. All right. Nope. Just doesn't want to let me select the erase tool. Well, what you have to do now is every time you do a branch to Bob or whatever, you have to put a no op after it. Yeah. And every Spark processor after that one had to support that, because otherwise the assembly code would not run correctly. And so every time you do a branch, you have to put a no op command after the branch. What happened if you did 2 branches in a row? It would run the second branch, and so you'd have to do branch, no op, branch, no op. Otherwise, you'd do the branch, then it would do the branch, which would be nonsensical, right? Or you'd waste the first one, right? So, yeah, and so that was a decision they made on one specific generation to squeeze some extra performance out of the CPU. And then because they made that decision, guess what? Every time you're given assembly code, like, you don't know, if it was written for that generation or that generation, so you just have to do it. And so all of these things build up, all these bad decisions build up over the years. And what happens is, you go from this to 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 this, and you've got to support all of the previous stuff. And so it's called cruft, right? Is that your code picks up cruftiness. In software, it's called cruft. And so if you have a software product, it's been around for 70 years or whatever, not 70 years, but since the 70s, your code's going to have cruft in it because one of the customers of your code absolutely needs this particular feature, and even though it's a dumb feature and you want to get rid of it, you can't because they're one of your customers and they give you guys $1 million a year, and so you have to just kind of support everything you've ever released. You know, if people use it and rely on it, then you can't remove it. And so as people add code to software, it's a lot easier to add code to software than it is to remove it, because you have to make sure you're not going to break something if you remove it. And if you remove it, then probably somebody was using it, and then you break them, and you have to put it back anyway. And so it's a lot easier for people to add new code to old code bases. If you've got 1 million lines of code in there, ain't nobody got time to read all that. You know, so what happens is like, oh, I need a matrix multiply function. All right, I'm going to make a matrix multiply function, add to the code. You know what? That code base probably has at least 3 matrix multipliers in there already. And so when you make a function called matrix multiply, it's like, sorry, that name's been taken. You're like, what? And then you like, matrix multiply 2, that name's been taken. What? And you check the documentation. In the 80s, a guy named Bob added matrix multiply 2 because matrix multiply 1, which is broken and is buggy and was written in Fortran originally, but is needed by your customers, is in there. So he created matrix multiply 2 that runs in C, that only works on 3x3 matrices. And so you can't overload it because it's written in C. And so, I don't know, you know, well, you could overload it in C++, I guess. But like, you know, so you make matrix multiply 3. Oh no, that one's been taken. That was created by a woman named Bonnie in the 1990s. And you're like, damn it, now our matrix multiply 4, you know, and it gets ridiculous. Like how many times people will solve the same problem in the same code base because they don't know that it exists in there already. A friend of mine was hired by the bioengineering department to do that. He was basically a code archaeologist, where you had generations of bioengineering majors that don't really know how to programming. And, well, I mean, they know how to program, but like, it's not like their thing. And so they just kept adding stuff and adding stuff and adding stuff to this heart simulation. And what he found was like, they would do the same thing over and over again. And so he worked on it for years, doing things like, all right, we've got 3 different things that do a partial differential equation. Let me just make one that replaces all 3 of them, and simplifying the code and shrinking it. And so his goal was to shrink the code base down. And that's something that you can do in software. In hardware, though, you're stuck with it. If you added a photo command, you've got to support that in all your future generations, even if there's no camera attached to your computer anymore, right? And so in hardware, if people are calling those assembly instructions, once you've added them, they're in, you know? And you could try breaking backwards compatibility, like with Itanium, but then nobody buys your product. So it's one of those things you have to think about. You have to think about it really, really carefully when you add features, because you want to add features to make your CPU faster, but you don't want to have to commit to that for the indefinite future. Okay. And so in the software world, a lot of times you can refactor and simplify and delete unused code. And in hardware, they kind of did something similar. So there was a big revolution in Intel's CPUs where it pretends to be an x86, but it's actually not. So what Intel does actually is it does something similar to this, where if you give it old x86 code, it actually will rewrite it into a different assembly form. And that all happens billions of times a second. So that's a lecture for another time how that works, but it's mind-blowing. Like, honestly, as much as I've dogged on Intel today, like the amount of genius that has gone into their CPU chips over the years, and AMD as well, is just nothing short of miraculous. Like, honestly, it is one of the most complicated things on the planet, and we're just kind of like, haha, Intel sucks, you know. And I kind of feel a little bit bad for them, but after my friend worked up there, and seeing how toxic their work environment was, it's kind of like, you know, let them burn. You know, let the garbage fire burn. You know, I don't know. Let Intel beat them up a little bit more. So, any questions about that, guys? So we had a kind of big, high level talk about generations of CPUs and stuff today. The midterm, we'll continue this talk on Thursday, but the midterm assembly, caching, bit operations. That's it. Multiple choice. You got to write a function, and you got to write. You got to debug a function. Okay. So that's it. Any questions? When's the midterm? Thursday. It'll start, let's say, after class on Thursday. So it'll be 2 p.m. Thursday to 2 p.m. Friday. That's the window. It'll be open. And once you start it, you've got a 2-hour block to finish it. Okay. And the timestamps on the server will be used to make sure you don't go beyond the 2-hour mark. We'll be posting any practice midterms. I don't know how close the topics are going to match, though. Because this year we're not doing any physical computing, right? So, let's see. Midterm 1 from last year. Translate the following code into ARM assembly. Translate into ARM assembly. Yeah, sure. Why not? Okay, so I'll put this live right now. And we'll call it practice midterm. This is from last year. If some of the topics you don't know, then don't worry about it. Because like I said, I redid the class. This access code off. Allow multiple attempts. See the correct responses. Tests. It's not going to be worth any points. Okay, so that'll give you some practice. Okay. Are you pulling some questions from the weekly quizzes for the midterm? Probably. Maybe. I don't know. The topics are these, right? So that's, you know, there have been daily quizzes that are, you know, based on these, but these 3 things are what I'm going to be testing on. Okay. Good question. Is that it? All right. If you guys have any further questions about the assembly, the midterm, let me know. And that's it for today. All right. Thanks, guys. See you on Thursday.